the equation that relates these two is probably, right, delta G equals delta H minus T delta S. Okay? So we have this delta G equals delta H minus T delta S. But we don't have delta G. Or do we? What's true at the point where a process becomes spontaneous? Delta G equals 0, right? So we actually have 0 equals delta H minus T delta S. Okay. If we're looking for T, we've now eliminated the one variable that was kind of causing problems. So we can just rearrange this so we get T. I've run out of T equals delta H over delta S. Okay? So now, given that delta H is equal to 55.5 kilojoules per mole, and delta S is equal to 148 joules per Kelvin, we should probably modify one of these, right? So that we have this in terms of kilojoules and the other one in terms of joules. So you can plug this in as terribly wrong. I see that. Where's this problem? All right, oh, okay. Never mind. I got it. I got it under control. Okay. So we modify this so that we take this decimal point, move it over, so that we get our delta S in terms of kilojoules. Okay. This T is then equal to 55.5 divided by 0.148. Okay. And if we do that math, we end up getting 375. Okay. If we look back at our set of answers, 375 is not there. What's the problem? Came out in Kelvin. Okay, so we take 375 minus 273 and get 102. Right? If you ever get answers that don't make sense, look at your units. You may not be as wrong as you think you are. Are there any questions about how to deal with delta G equals delta H minus T delta S? Yes?
I think, is that, oh, it's 55.5?
Yeah, it's 55.5. Okay. Yeah. All right.
Okay, moving on to some electrochemistry. We have a constant current of 3.2 amps is passed through a solution of AaUCl4 between two gold electrodes over a period of 20 minutes. What mass of gold was deposited on the cathode? And we're given Faraday's constant, and we're given the molar mass of gold. Now this question is helpful for other questions on the exam, because if you forget, where does reduction take place? This tells you. So we're reducing that species, right? Because we're adding electrons to it, and so we can remember that reduction happens at the cathode. So that's something that you can remember for later on in the exam. All right, so anyway, onto the equation for what we're doing here. Okay, 3.2 amps. So we have to remember what's the relationship between a coulomb and an amp. We know that it's a charge per unit time, right? So that means that a current is the amount of charge per time. Or in other words, coulombs are amps times time. So what we can say then is we say, okay, specifically seconds. So we need to convert 20 minutes into seconds. Into seconds would be times 60. So 20 times 60 would be 1200. So over a period of 1200 seconds, we're going to take 1200 times 3.2, because then we can rearrange this equation to say then that into that, and then we can say then that 3.2 amps times 1200 seconds gives us number of coulombs. Okay? (38, 40 coulombs. Okay. So then we have to decide, okay, so we figure out how many moles of material can we deposit with that amount of charge. So we look at Faraday's constant and we say that, see that 96,500 coulombs is in 1 mole of charge. Okay? Looking at the equation, we need 3 electrons to make 1 mole of gold. Based on this equation here, that 3 moles of electrons give 1 mole of gold. So then what we do then is we say, okay, so how many moles of electrons do we have here? So we can say 3840 divided by 96,500 coulombs per mole gives the total number of moles of electrons in that charge. So we take 38 divided by 96,500, 0.040. Yep. That many moles of electrons. So we take that number divided by 3 to give the number of moles of gold. Okay? convert that into mass. 0.013 times 197. .6. Any questions on this one? Okay, moving on.
Okay, so we're pretty close to the end of this. Since exam 3 was so nearby and everybody's covered it, we're going to quickly do 1 or 2 problems from each professor's final lecture section, just to run by that real quick. And then we'll open the floor to general questions. Sound good? So, I'm going to run through one problem. Leopold's section, correct me if I'm wrong, right? You guys have done transition metals and nuclear sign and nuclear reactions, things like that. Okay, so I'm not totally off here. Okay, sweet. Look at this. Which of the following metal ions is most likely to form colored complex ions? So if we put some ligands on these things, which compounds will be colored as opposed to not? The main thing that governs color in metals, right, is the d-d transition. Okay, so we have a transition between different sets of d orbitals. And this question is actually deceptive. It's a little easier than it looks. So first off, the thing you want to do is go and look at how many d electrons each one of these things is going to have, right? And that requires just kind of look at the big periodic table over there, right? And count from the left over, and that gives us the total number of electrons, right? So like calcium, well, if you look at potassium and calcium, those are going to be S. But then as we go to scandium, titanium, right, we fill the orbitals first. And so, scandium in the 0 state, for example, this first one, in the 0 state has 3 d electrons. Okay. However, it's scandium 3+. So all those electrons are gone, and we don't actually have any d electrons, right? So how can we have a d-d transition? Right? That's gone. If we look at the next one, way over at copper, okay? Copper is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over. So we have 11 electrons. We're 3d10, 4s1, right? If we give it a +1 charge, we take off 1 electron, we're at d10. So copper's d10. Now the question is, if we have 2 different levels of d electrons, regardless of what, did you talk about crystal field ligands, things like that? Okay. Regardless of which geometry we have, we're going to have some set of levels. And in order for there to be a transition between those levels, you need an empty orbital, or a half-filled orbital, someplace for an electron to go. If you're d10, there's no transition available, because you can't excite an electron to a filled orbital. So that one's not going to have a d-d transition either. We look at Zn2+, same situation, right? It's next to copper, except this time we're oxidizing the 6 electrons with 4s2, 3d10. We take off the 2 4s's, and we're left with 3d10. Okay? Calcium on the bottom should be just silly, right? It doesn't have the electrons even in its natural state. Well, it might, but it's oxidized, so we don't. Or sorry, yes, it's oxidized. So that's gone. And we have this chromium complex, which if you've gone through and eliminated the rest of these, you can tell it is the right answer. But just to double check that, it's got 6 d electrons. We take off 3, and we're left with a d3 complex, which is only going to fill, regardless of your splitting, whatever it might be, we have some transition there. Make sense? All right. Are you?
I'm not even.
Not quite yet. Okay. So I can write up one. Where did it go?